Okay, so we're going to go over states of matter and heat curve of water. So just a reminder for states of matter, right? We have our solids. Remember that these, they are moving, but they kind of stay in place and just kind of vibrate, right? Just in place like that, right? So this guy will stay here. He won't move over to here, but he does kind of sit there and vibrate. And so the reason for this, remember, is that these are a lower energy state of matter. And so they're all like kind of just stuck together. They don't have enough energy to move away. And then remember, as we add heat energy, let's go ahead and add that now. Remember, this is energy, okay? So we're adding more and more energy to get to these different states of matter. So as we add more energy, remember this solid is vibrating. As we add more energy, it vibrates harder, and eventually it kind of breaks free, and it can start flowing and moving around, and that's when we get our liquid. It doesn't have enough energy to like jump up and fill the whole container, but it kind of just settles at the bottom and kind of moves around, sloshes around. You can pour it and stuff like that. It's still very close together. Liquids are still very close together. You can't compress them or anything like that. But they are moving around, and they do have more energy than solids. As these liquids are moving around, if they got even more energy, right, you added more fire, they start getting crazy, they get fast, and they jump up, right? And so these things are just bouncing all over the place, right? Just hitting the walls, hitting each other, bouncing away. And so these are very, very, very high energy, okay? So this will be the highest energy that we talk about. Remember, there is plasma as well. We don't really go over that too much, but even more energy, and the particles start to rip apart into charged pieces, right? It's crazy. So gases are high energy, solids are low energy. Really far apart, really close together, pretty darn close together, but can slide past each other, okay? So that's states of matter, not too bad, right? And then remember, we call it melting and freezing is at the same kind of temperature, right? We'll talk about that in the heat curve graph. And then remember, vaporization is basically boiling, right? And that's another important one to pay attention to, okay? So if we look at this heat curve then, it's kind of showing a similar thing, but with a graph, right? So remember, every time you look at a graph, kind of pay attention to what your labels are. So we have temperature on the y-axis here, and then we have heat energy on the x-axis here, right? And so we can just follow, as we add heat, right? We see the temperature of the water going up as we add heat energy, okay? And so it starts at this low heat energy as a solid, right? And we would call that ice for water. As it gets more and more energy, it starts to get to this point where it'll start to melt, right? And so we call that the melting point. And if you look at your temperature for this chemical, that would be a melting point of 0, right? Notice what's happening here. It's a flat line, right? The temperature is the up and down. It's not going up and down here. So for this whole spot, the temperature is not changing, right? Until all of the ice melts, the water will not get hotter than 0 degrees. Once all the ice melts, then the temperature will start going back up, okay? And so for this whole phase here, we would have a liquid, and it just goes up and up and up. Once it gets to this spot here, we notice that it flattens out again. And then we notice that it's vaporizing here, it's switching. So it's a mix of liquid and gas here, which we call boiling. And if we look here for water, that boiling happens at 100 degrees. So that would be called the boiling point. And then notice the temperature here again. Is the temperature going up or down? No is the answer. It's not going up or down, it's staying the same. So water that's boiling will stay at 100 degrees until it completely goes into a gas, and then you can start raising the temperature. Remember, an easy way to remember this is we use this in cooking. For example, if you're melting chocolates or something, you stick them in a pot of boiling water because they will never get above 100 degrees Celsius. So your chocolate will melt, but it won't burn. So useful thing here is when things are switching states of matter from one to another, they stay at that temperature until they've completely changed to a new state, okay? So remember here, we would see a combination of solid and liquid. And then here we would see a combination of liquid and gas, right? And then eventually we'd get all gas once we have the highest heat, highest temperature, gas, okay? Now, another thing to consider is that as we go from a solid to a liquid, right, we're saying that there's more heat energy, right? If you're at a solid, right, remember, your particles look like this, they don't have much heat, okay? If you want to get them to a liquid, right, they'll start looking like this, where they're kind of slightly more spread apart, they're moving a little bit faster, they're sliding past each other. Well, the particles must have gained energy to do that, to go from a solid to a liquid. They must have gained energy. Whenever something gains energy, it takes it from things around it. So if you hold an ice cube, it steals energy from you to melt into a liquid, and that feels cold to you. That's because it's endothermic process. The ice is taking energy, right, kind of like this picture here, right? The ice is taking energy to melt, right? So the ice is getting more energy, but it can only do that by taking the energy from things around it. So if you're holding that ice, it feels really cold. Your heat's leaving and going into it, right? So remember, that's endothermic. The reaction is absorbing energy. So anytime we're going in this direction, that's an endothermic process. Remember, going from a liquid to a gas, those particles are gaining more energy. That's endothermic. Now, what if something's cooling off? Well, liquid to solid, right? So if you put a cup of water in your freezer and freeze it to a solid, all those particles where they had high energy, they were moving around like this, and then they slowly kind of slowed down, and just kind of vibrate in place as a solid, right? So that would be an exothermic process. In order for these to lose energy here, they have to spit their heat energy out, kind of like this graph here, right? The water has to lose heat energy in order for it to cool off and become ice. Now, you think of a freezer as cold, so it doesn't really make sense, but if you feel the back of the freezer, it will feel warm, and that's where all the heat is going. The freezer pulls the heat out and puts it off into the back of the freezer, and that's what you feel in the back of the freezer. It's all the heat energy that was in your water that's being lost to turn it into ice, so it cools down from a liquid to a solid. Same with a gas, right? If there's steam and it cools off into a liquid, it has to give off energy, okay? So that's all of these processes would be exothermic, right? They're losing heat energy, which means the heat energy has to be going out into the environment. So these would feel hot, going this way would feel cold, endo versus exothermic, okay? This is a huge part of your test. All of the things that I just talked about with states of matter and this heat curve and exo and endo, huge part of the test. One thing to keep in mind is that if it asks you which of the following is exothermic, for example, there's a whole bunch of options here. Going from A to B is not exothermic, but it would be endothermic, right? If it's asking for exothermic, any of these, E to D, E to C, E to B, right? C to B. Any step where it's going from a higher energy step to a lower energy step, right? Even if it skips around, those would all be exothermic. And the same in the other direction. If it's going from A to B or A to C or B to E, any step where it's starting at lower energy and getting more energy, that's an endothermic process. So you have to mark all of those that would be correct. Okay? All right, that's it.